Okay. All right. Sorry about the delay there. We just had a computer shut down here, so hopefully I'm not going to do anything too nasty to it or whatever. And so we're going to talk about exercise 5. I don't want to say quickly, but I just want to make sure we know the why behind everything. Why do we care about quadrant analysis? That's the thing, because we've migrated into inferential statistics. So we migrated into inferential statistics because we want to see how they compare to random. Because when we look at these points up here, first of all, what does it look like to you? Ahmed, what's it look like to you? Okay, so just a bunch of points, right? I don't know, just a bunch of points to me. And so some of these are close, some of these are far or whatever. So the whole idea of nearest neighbor analysis and quadrant analysis, and especially quadrant analysis, so we can visualize these patterns, because when we throw up all of these points, let me just throw them over the back of my head. How do these compare? And so we decided to create something called the quadrant right here. Now, they require the use of some existing GIS skills, or those of you kind of learning GIS as we go, some kind of rudimentary skills where we do a little select by location, we do a little extraction, and then we do a little fishnet, we do a little spatial join and summarize, and then kind of bippity boppity boo. Bippity boppity boo, we've got something up there that looks good. It looks like a graph here. And so real quickly, what we're going to do is we're just going to look at Caswell County right here. Hopefully everyone can see us. My computer's starting to act a little funny again. I think I'm just running a lot of things on it. That's the problem with it. And it's getting a little old, so we're going to have to probably part ways soon. Okay, but I've picked out Caswell County, and I'm going to do select by attributes or select by location. So I can do a select by location. And all I want to do is just find all of the deer vehicle collisions that intersect with these counties. And so I'm going to be working with this set of this set right here. So I can extract out the county as well as I can extract out these data sets here. So the counties, I can right mouse click. I can go to data, export features. And I'm just going to call this thing Caswell County. And then the deer vehicle collisions. And we'll just call these Caswell DV. And we're going to uncheck everything else here. So we got Caswell County. We're going to uncheck everything else. So all we're going to be doing is doing some quadrant analysis for this thing right here, just for this right here. And we had an equation. It was the square root of 2 times a over n. Is that right? Yes, that sounds right. All right, where do I get the number a from? The area. What's the area of Caswell County? Well, let's click on it. Maybe something will pop up that gives us the area. And if I go all the way down here, I have a feature attribute called square miles. It's 428. What are the number of features within it? I can right mouse click on deer vehicle collisions, open the attribute table, and we can see there is 115. Now, the one thing about this, we kind of learned this earlier, is that, do you see 115 points up here? There might not be 115 points up here, but some of these might be lying on top of each other, might be coincident points. And so when you run your spatial joins later, you might see that, hey, this thing says it has 6, but there's only 4 there because we've got some coincident points on top of each other, depending upon how they were coded. Like move to the nearest block or whatever. If a crime occurs on this block, we don't put it on this location. We just put it at the block. So we've got a number of different kind of crimes at this particular block here. And you can see here, they put them at mileposts, distance and direction. So you can see, you can see the granularity or the precision at which we map these. And so we've got this kind of calculation that we have right here. And so this quadrant analysis calculation, so it's 2 times the square root of 2 times a over n. And so I'm just going to do my little calculator here. And so 2 times 484 equals this, divided by n, which is 115, equals, and then we kind of take the square root of that, right? And so it's like 2.9 miles or something like that. Does that sound right? Let me double check on this one here. I'm looking that up right now because I don't even know it by heart. I just refer to everything and go from there. I'm looking here. Here we are. So here's our quadrant analysis here. Poisson. Here it is. Okay. So 2 times a over n. So 2 times the area over n. Okay. So the length of each of these quadrants or fishnets or whatever. What I'm going to do here is multiply this by 5280. So times 5,280. And it equals about 15,000. And that's the number of feet, the length of each quadrant. Because you notice right here, I put an example of a bad fishnet right here. Why is this a bad fishnet? Because what I want to do is count the number of deer vehicle collisions within each of these squares. Why is this a bad idea? Why is this bad? These are some of the things I was talking about with Benjamin before. If I'm making a map with like 2 stores on it, is that really a map or 2 counties on it? No, why not? Because like we want to look at 100 counties to see where the differences are between those. And so when we make a map, a bad fishnet that looks something like this, there's only like, I don't know, 18 of them here, and we're looking at thousands of points. And so what we want to do here is kind of focus in on this. We use this little formula right here, and I'm going to go and create a fishnet. Okay, so I'm just going to superimpose a fishnet on top of this. So I go to Analysis, Tools. If I don't know where to find fishnet, what can I do? Just start typing the word fishnet. So I can create a nice fishnet right here. My output feature class, I'll call this Caswell fishnet. And then my default I'll use is just Caswell County. So this is kind of my default extent. What are all these numbers that just popped up? Coordinates in what? What do these matter? Are these in degrees? No, these are in feet. And so now when I say cell size width and cell size height, what do you think? Are these going to be in miles or are these going to be in feet? Feet. So I'm going to type in 15,318. I can make these squares or whatever, 15,315. I don't want to create this, and I want to create polygons because we're going to do a nice spatial join right here. Output feature class. Now I can run this. And so my question is, what is this, the real significance of this 15,000? Why did we create this 15,000 here? What was so important about this 15,000? Yeah. Why?
which is the size.
Yeah, what, so that formula, we use that. Why did we pick that formula? Because it creates a good enough size so that we're gonna have a lot of squares that have something, but we're gonna have enough squares so that we have spatial spatial regionalization throughout the map, right? Because I don't want really tiny ones that have lots of zeros, but I don't want to have really big ones, so that I only have like 4 of them here, so we really don't have a map. Now, the next thing that I want to do, I want to count the number within each. How do I count the number of points within each one? Spatial join. And so now I can run a spatial join. In the tutorial that I provided, you notice that I kind of went through all these caveats where I got rid of the edges and all that other stuff. Let's forget about that for now. When you write a paper or do some research, people like me will ask those questions. But for now, we'll just run a nice spatial join that counts these. Okay, we all know how to run spatial joins. We've been doing it since week 1, where we counted the number of cancer deaths by counting. And so if we have a little trouble with that, that's going to probably be, that's something that we're going to need to play a little catch up with. And so we got the Caswell fish, net. The join features are going to be the Caswell deer vehicle collisions. Well, let's see what we got here. Right mouse click, open attribute table. Now it's all just sitting right here in one attribute table. So look what we have here, join count. So now we got 64, we got a 6, a 6, a 5, a 5, a 4, 4, 3, 3. We got a whole bunch of zeros right here. Okay, whole bunch of zeros right here. Now I want to count this frequency, so I'm going to create a summary table. What does a summary do? Who said that? Well, we're going to run a summarize. Now look what I have here. Okay. I'll do it the other direction here. So now when I run this, I've got 19 have 0, 16 have 1, 8 have 2, 10 have 3, 4 have 4, 5 have 5, 2 have 6. Now, can I make a nice pretty graph out of this? Of course I can. Can I graph this? Yeah, definitely. Watch this. I can make a nice line graph out of this. Go to insert, graph. For now, we'll just do this. What are the chances? This is the distribution. How can I figure out what this compares to? What can I do here? I can run a nice Poisson distribution. And that's what a Poisson distribution does. With the join count, I can do a Poisson distribution. Okay, so I can type in the equal to sign. I can type in the word Poisson. What's the X? What's the mean? Now we're getting deep here. What's the mean here? Average number of, can I figure out on average how many deer vehicle collisions per cell exist? How many deer vehicle collisions are there? 115. How many cells were created? How many rasters were created? 64. What's 115 divided by 64? Less than 1.79. So on average, there should be about 1.8 points for every cell. We know, because of rounding errors. So in theory, when we look at this, 16% of them should have a 0. 46% should have a 1. 73% should have a 2. Oh, actually, this isn't cumulative. Sorry about that. I got to do something called false. %, 29%, 26%, 16%, 7%, 2%, 0.007%. How does that compare? So on a Poisson distribution, it should be 11, 19, 7, 10, 5, 2, 0. It's really 19, 6, 8, 10, 4, 5, 3. How do these graphs compare to each other? Can we put these graphs right up next to each other? You bet. I'm on the spot here, so I've got to figure out how to stick another graph up here. This is what it should look like. This is what it really looks like. And you can superimpose these on top of each other using different data sets, but on the left is what it should look like using a Poisson distribution. He's just throwing 115 vehicle collisions up there. This is what it really looks like. What does that tell you? Does it tell you anything? We're taking this stuff for the first time, so it tells me that they're kind of far off. You can see the peak is over here between like 1 and 2, because this is 0, 1, 2. So the peak is between 0 and between 1 and 2. Does that make sense that the peak's between 0 and 1 and 2? Yeah, it should be, because it's an average of 1.796. Here, the high is at 0. 0 is the highest, and it works its way down. And so when we look at these or superimpose these on top of each other, this is what it looks like. Me personally, I like these graphs. The reason why I like these graphs is because it kind of visualizes these points. And then you can do one for Rockingham County. Rockingham County might be a little bit closer. Okay, but I like this quadrant analysis. It takes a little getting used to. The one thing about the GIS is that we've covered all these skills. The thing is, you got to put one skill on top of another skill on top of another skill on top of another skill. Because a lot of times in my 34, 35 classes, a lot of people tell me, what button do I need to click to get the answer? And eventually, when you get to 4010, it's like, what 3 buttons do I have to click in successive order to get the button? Now we're at a point of, all right, what 5 buttons do I need to click, or what 5 skills do I need to do in order to kind of successfully do this? So today, we are going to talk about hypothesis testing. I really like this chapter because this kind of is where you put your money where your mouth is. Meaning we can start to make concrete statistics about things. Okay? And so these are some examples. This is kind of where you earn your big bucks. Okay? Meaning you're doing air quality testing when we make these statements like, air quality is poor or worse in poorer neighborhoods than richer neighborhoods. These are the tests that you use to support that. These are the tests that we're going to use to support that. So is there a difference between cancer deaths within 1 mile of point source pollution versus outside of 1 mile of point source pollution? Why did I pick 1 mile? It's just a nice, pretty number, but you could define the word near. Is there a difference between school achievement in rural versus suburban versus urban schools? That's always been a kind of a hot button topic here. How are socioeconomic indicators for high food accessibility versus low food accessibility? And we're going to look at some of those today. And then in class, after our break, we're going to look at a case study where we're going to see, are COVID rates higher in rural regions versus urban regions? What do you think? What do you think, Sanaya? COVID rates here. Yeah, maybe. I don't know. We'll find out. Okay. And it's also going to be time dependent. What's the definition of rural, first of all? 15 different definitions. But we're going to pick a really general one. And then how do cancer rates compare to places near Superfund sites or brownfield sites versus those further away? I got lots of examples. Do deer vehicles exhibit a Poisson distribution? How can we tell? This is just kind of what we looked at. Are minority heart disease death rates significantly different than majority death rates at the zip code level? Or by-mail voting patterns higher in COVID-19 hotspots versus COVID-19 cold spots? So I'm going to show a couple examples that we have here. This is some of the work that Dr. McGinn and I have done where we looked at by-mail voting rates for North Carolina. This is the percentage of people who registered voters who voted by mail. They literally mailed in their vote. They never showed up at a polling place. This information is spatially distributed. I like this. You think of any phenomena out there, things like sex ratio or by mail voting, or lots of these things that you think of might be random in nature, and they're not. And so we can look at this. Another thing that we can look at around the time of the 2020 general election, this was the COVID-19 incidence rates. And so what I can do, and we're going to talk about this in about 2 weeks, is that we're going to extract out hotspots. Okay, these are hotspots. These are high values divided by or surrounded by high values. What's the definition of high mean? And I kind of keep pushing this to people. I've said this before. What's high mean? Positive. Above average. Do we know how to calculate average? You bet we do. This is what we spent the whole first half of class doing, average. Okay, today we're going to talk a little bit about variance. Okay, so clustering. So high values surrounded by other high values, low values, and obviously low is going to be below average. We all know how to calculate average. We can see here we've got 763 zip codes, so we just averaged up the COVID rates for all 763 zip codes as of October 31st, Halloween 2020. That's all we did. And so all we're going to do is, how are the by-mail rates here versus the by-mail rates there? And we're going to look at this with statistical significance. Some issues to consider. Okay, rates are going to be necessary when we have like COVID-19 rates, by-mail rates, median household income. So things that are going to be normalized. We spent a whole chapter this semester talking about the idea of normalization. Be sure to maintain consistency. One of the things that I'm going to look at here is something called PRTI. It just stands for Pixel-Based Relative Travel Time Index. All it is a ratio. What are other ratios that we've talked about in this class? What's a real big one? Measure of dispersion that we've talked about. Z-score, right? Isn't Z-score just a ratio? Okay. And so this is a pixel-based relative travel time index. It's going to impact rural versus urban a little bit differently. So this is PRTI. We don't really care too much about this, but the red areas in this map here in southeastern North Carolina are much closer to fast food than healthy food. The green areas have better access to healthy food compared to unhealthy food. And so you can see this. And basically, I picked out all the rural areas because the dynamics for urban areas are going to be entirely different. And so I kind of, you see how it kind of looks, you know, we're missing all the rural urban areas here. And so you can see that it's normalized. So when I go through and like calculate these travel times, you can see it still exhibits a normal distribution, although it's skewed to the right a little bit. And so, yes. It stands for Pixel-Based Relative Travel Time Index. All it means is that for each of the zip codes, it's the ratio of distance to the nearest healthy food to unhealthy food. So when we see these things in red that are 1.5 to 3, these things in red, people have to travel 1.5 to 3 times further to get to healthy food, supermarkets compared to fast food. I used raster, yes. I created a cost distance surface. I could really go off in the left field on this, but we have a whole paper on the creation of cost distance surfaces. The same thing you do with your phone, but we created cost distance surfaces. You only have to create it once and then extract them. It takes a long time to run them, but I never have to run it again. Where that you go and calculate travel time, how many times you do it. You do it a lot when you need to do each of these individual things here. And so these areas in red have worse access to healthy food. Areas in green have better access to healthy food. Now, we can start to make some assumptions being like, hey, how do these areas in green, the income of these areas in green compare to these areas in red? Meaning, like, do the rich or the white or whoever else have better access to these green areas than other folks here? And so we can start to look at different areas here. And so when we look at the better access, we can see the median household income for the people in green is $37,000. The people in red is $33,000. They're more. Now, is it that much more enough for me to say it's statistically more? Maybe. It's getting close. We'll see. Other things, and this is taken straight from the paper that Dr. McGinn and I did, is that when we look at the highest minority zip codes, we look at, I think these are by mail versus COVID rates or something like that. But we can see right here where the highest minority rates have really low by mail versus highest majority zip codes. These are by mail rates. And so you can see here that minority or disadvantaged communities actually mail in their ballot at lower rates than majority white. Do you think that's a coincidence? I don't think so. Now, what are the reasons out there for? Redlining, people aren't provided with the resources, access, all these other things. I don't think it's just a big conspiracy that said we're just going to mail it in, or whatever. Okay? And so we can see now, are these going to be statistically different enough? Because with hypothesis testing, it's an important component of the scientific method to test hypotheses through experiments or predictive forms of analysis. We'll get into predictive analysis in a little bit, but a hypothesis can be defined as a tentative assumption that is made for the purpose of empirical scientific testing. This word empirical, has anyone heard this term before? It stands for measurable, things that we can measure. And while I'm thinking of it here, I had a whole bunch of papers before my computer died that, or went out or whatever it decided to do, but I'll put a couple up here. But a lot of times when I write papers, one of the big things I do is that right in the introduction here, I put my little hypotheses that I'm going to go through and prove. We will explore the difference among various applications of the term rural. Now, what's the whole goal of this paper? I have another one here that we talked about. How do you open these days? Okay, open. Oh my gosh. Okay. This is the paper that we have here. We have it right here. Working thesis that regions with higher COVID-19 rates will have higher buy mail rates. This is taken, straight from our paper. This is what we look to prove or disprove. And one of the things that I do these days with my papers is that somewhere in bold or somewhere at the beginning or somewhere numbered that I'm going to state my working hypothesis that I'm going to prove or disprove using the methods that we have, or using the methods that we're going to focus on. I think I have one more here. No. Okay, this one right. And then here's one here. These are all things that you've read before, where that look at places where rural food security is a problem. If rural food security does exist, where does it exist in North Carolina, and what ages, races, and ethnicities may be impacted most by rural food security, or in this case, insecurity. And so we've got the whole idea of hypothesis testing. Now, some things need to happen. Okay, we have type 1 effects, urban heat islands. Is there a significant difference in temperature between urban and adjacent areas? We'll get down a couple of these rabbit holes both this week and a couple of weeks when we talk about what's the word adjacent mean or neighbor mean. These are all things that could be measured spatially. Or we can look at crime rates. What are the crime rates? What is the average crime rate for this group of neighborhoods versus another group of neighborhoods? Because the key questions in statistical significance are, what are the probability that we think the relationship between variables is just chance occurrence? Okay, just chance or occurrence. What are the chances that the findings are not true? And so what do our tests tell us? The probability that statistical relationship we think is found due only to random chance. I'm going to make a hypothesis, and I'm going to say that the professors on the NCCU campus are taller than the students on the NCCU campus. Well, Lauren, why don't you stand up? Look, I've proven my hypothesis. So is that right? Benjamin's shaking his head no. What? You don't have enough data. I don't have enough data. Okay. That's the term that we kind of deal with here. Now, if I were to do it with 2 people, well, we'll see. What about 5? What about 10? What about 100? What about 1,000 or 10,000? Well, if we did the whole campus, it'd take a long time. So we need to find a happy medium between finding an adequate sample size, random sample size, and so we can run our tests. And we're going to see a lot of these coming up in the next year with this election stuff. With 46% plus or minus 3%. What is that plus or minus? How did we come from that? And so we can never be 100% certain that a relationship exists between 2 variables. There's too many sources of error, meaning we just happen to pick someone who is shorter than me, but if I were to go to Benjamin to my right, well, he's taller than me, so I've just disproven my hypothesis here. And so a lot of times we call that the exception fallacy. And, has anyone heard that term? A lot of times when you state a fact and you say, I know someone who ... a lot of times I hear about this with my kids or whatever. My kids who got terrible grades in high school, and they're like, well, I know someone who got bad grades and did this. And you're like, okay, great, but what do the statistics really tell you? Statistics tell you higher grades, higher success, however you measure, income, happiness, whatever you want to call it. So that's what we call the exception fallacy that we'll talk about later. But we talk about the idea of we have a statistical inferences from sample size. So with statistical inference, okay, how do they compare to random? How do they compare to each other? Is that you have a random sample. Now, can something really truly be random? Okay, what's a random sample? Random basically means it's got an equal probability of being included. Now, by definition, to me, most of the things that we have are not necessarily random or representative. One of the things that we did with Durham County is that we're sending out these surveys in the mail, and you fill out a little QR code, and then you answer questions about your water quality. do you know how to test your water and all that other stuff? Did I talk about this before? Oh, maybe not. Okay, but they go test out. That thing is going to be, that sample really truly isn't a random sample. Why? We're going to get all these answers and we're going to get all these data and we're going to say, 82% of the people think their water is good, 3% think it's poor, 87% know how to call the county and report a water problem. But why isn't that a truly representative sample? Do you think my grandmother can know how to turn on her phone and get a QR code and send it to survey? No, not anymore, definitely, but no. Okay. And so these truly aren't representative. And a lot of these, in this day and age where we have these polls, how are most of these polls taken? Digitally. There are people out there who have little access to broadband, digital, all these other things. Even though these things we carry in our pockets, there's whole groups of people out there, like my friend's dad, he's still got a little flip phone. You guys know people who have flip phones? Yeah. He refuses to do it. There was a professor I knew over at UNCG, had a little flip phone. He didn't want to get anywhere near this stuff. Okay. So you could get lucky or unlucky, meaning that I'll just go measure myself against Lauren and say I'm taller to prove or disprove my hypothesis, but we want to get a bigger sample. Now, we don't want to sample all 8,000 people on campus because that's going to take too much time. Just the same way that we're not going to go poll every single person who walks out of a exit poll at an election to say who they voted for. You get a good idea and then move from there. Because typically when we work with sample data, and the census is a good example of sample data, is that we might look at like median household income. We have something called the margin of error. Has anyone heard that term before? We'll get used to it in the next year or so with all these areas, with all these polling. And so we have confidence interval, margin of error divided by the estimate number of people here. So basically, our confidence interval is going to decrease as our sample size and our estimate increases. Okay, and that makes sense. And so a lot of times when we look at Esri data, we make it high reliability data, medium reliability data, low reliability data, where that if we're asking for how many Danish immigrants are in this census tract, well, there's not a lot of Danish immigrants in this census tract, so your margin of error is going to be relatively high. And so when we look at census data, we really need to think critically about how reliable are some of these data. Now, when we start to answer some of these questions, some of these things I want to do, I want to see if median household income is the same for the highest quantile or quintile of access versus the lowest quintile or quantile of access. Why? We can do a test of two means. So I can kind of authoritatively say that higher income people have better access to healthy food compared to lower income people using these measures. So we need to qualify these for Southeastern North Carolina. So we can go and prove and disprove these statements. Temperatures are higher around cities than non-cities. We hear these statements all the time. You open this thing up and hear fact after fact after fact kind of given to you. And I think we know about the data. They're pretty unbiased, but I think sometimes the techniques are a little bit more biased. Some of the things we need to do is that we assume the median household incomes are the same. Meaning, all right, for all those areas in green, we're going to assume the income is the same as the areas in red. And so we're going to run, that's going to be what we call the null hypothesis. Has anyone heard that term null hypothesis before? Well, you just heard it. Okay. Now, I have one of the papers there in under module that looks at the cancer death rates where we explicitly state the null hypothesis. Now, you notice in my paper with Dr. McGinn, we said my working thesis is that these areas are going to be higher and lower. That's what we basically said. We said, hey, we're going to assume that the COVID rates are going to be equal, or the by mail rates are going to be equal in one area versus the other, and then we're going to hopefully prove or disprove these. We have something where we prove or disprove called the alternative hypothesis, where it says the average is more than the other. Okay, so does it matter higher or lower? It doesn't really matter here. And so when we look at this, the best axis has a $41,000. The poorest axis has $32,000. We ask from standard sampling alone, basically me going out and just averaging my height and all the other faculty members' heights versus students' heights, what are the chances that we're going to have an $8,500 difference? So if I were to get 50 faculty versus 50 students, we're probably going to get some difference. It's not going to be exactly the same, but what are the chances we get a 2-inch difference between faculty heights and student heights? We can maybe start to say, hey, faculty are taller, or students are taller, or whatever. What are the difference that we have $8,500 difference between these, just gobbling up, getting 40 random faculty, or in this case, 11 random block groups. Okay, is it reasonably probable or likely to accept the null hypothesis, or do we reject the null hypothesis and accept the alternative hypothesis? And I'm going to talk about how we word these, because when you get into some of these research papers, people get really emotional about how you word these and the word statistically significant. And so even though I have trouble with these as well, because when we look at normalized data, at the end of the day, all we're looking at is a normal distribution, right? And so we have a normal distribution of the good axis, a normal distribution of the bad axis, and let's see how close these means are to each other. Because if these means are really close to each other, we can't say there's a difference in good access versus bad access. We can't say rich people have better access to healthy food compared to unhealthy food using these measures we have. We can't. There's lots of other reasons out there, or maybe there are no reasons. Maybe it's random or stochastic or whatever. Maybe rich people don't even care about living close to healthy food in the first place because they don't care about driving or whatever. They can Uber it or Uber Eats or whatever it is home because they can afford to. So all we do when we run a two-tailed t-test is that we run these distribution curves, and if these things are far enough away from each other, we can say, yeah, they're statistically different. I've got a calculation here. Don't worry about this. The only thing that I care about here is this N. This stands for sample size, meaning if you get more samples, you're going to get smaller margins of error. That's all it means. And so now we're not going to do sample size 1 where I'm comparing my height to Lauren's height. We'll get a sample size of 10 or 50 or 100 or 1,000 to compare these so that we get much, much smaller margins of error. Okay, the one thing that I do like to do in this class is I don't like showing formulas. Now, when we run this in Excel, we're going to do this after the break today in Excel, where I run it, where I see the best axis is 41,000, the worst axis is 32,000. I get a sample size of 11. I get this Pearson coefficient. What I focus on right here is this p-value, 0.03. What do you think the word p-value means in statistics class? What do you think, Alondra? Alondra's looking in the other direction. She said, p-value. What do you think p-value means? What have we been talking about? Probability. And so the lower the p-value, the more significant the difference here. We have these t-values. These t-values typically align with your z-scores. Remember that z-score and how far away from the mean it is? And so these p-values align with these t-values on a normal distribution curve. Okay, so you can see these are pretty far away from the mean or what we'd expect. This is what I care about. The lower this, the more that I can say that these are statistically different. Okay, but lower numbers better support my hypothesis that they're different. In some cases, I want them to be the same. Do I really want to say that access is determined by race or income? I don't want to say that, but what does the data here tell me? You bet there is. Okay, and I can say with like 96% confidence, and I'll talk about what that means here, where that means that it's highly unlikely that the means are equal and we accept the null hypothesis, meaning that if I were just to grab 11 random block groups and another 11 block groups, there's very little chance that the average incomes for these 11 are going to be $8,000 more. Okay, that's a big difference. $8,000. It might be $1,000, maybe $2,000, but $8,000. There's something else going on besides random chance. Okay, and that's the whole idea of inferential statistics. What can we infer from those? These are not due to random chance. Okay, that's the important thing here. Okay. And so we've got these normal distribution curves. And so when we start looking at these z-scores are out here or out here, these p-values get really, really small. Okay. Okay. And I don't want us to worry too much about these, but they get out here because essentially all we're doing is comparing two normal distributions and then seeing how far away they are from each other. And I let Excel tell me how far away they are from each other. That's all we're doing. So if they're far enough away from each other, we can say that the means are statistically different. So you can say, hey, air quality in low-income neighborhoods is worse than air quality in high-income neighborhoods. And so if we go and get the air quality for the 25 low-income neighborhoods, go get the air quality for the 25 high-income neighborhoods, we can average those up and see how they compare to each other. Maybe there's other things going on with air quality or water quality or whatever. And so when we get on these ends, we reject the null hypothesis, accept the alternative hypothesis. What can we say? The median household income are different. In this case, they're greater. The best access has higher household income than the worst access. And so these are some of the assumptions that we can make from these. These are going to be some of the assumptions. Okay, so to reject the null hypothesis, the z-statistics has to be greater than negative 1.96 or 1.96. I wouldn't worry about this. What I worry about is what does Excel tell me? And that's what we're going to work on today when we're done here. And so there are many ways to say the same thing. People, like I said before, people get very emotional about how you word statistical significance. And in this class, I'm going to say that the results are statistically significant at the 5% level, or we are 95% confident that they are statistically significant. They are significant at the 95% confidence level. So you'll see a lot of our papers highlight that. Here's an example of a non-significant result, meaning we're looking at COVID rates, and when we run it, we get a p-value of 0.595, meaning one's 393, one's 422. They're different. They're not different enough for us to say they're statistically significant. Previously, I had the equation for that, which was based on both the sample size and the variance. What does variance mean? Variance. Who's scratching the brain here?
Like if we do like housing income, like how far it varies.
How far it varies from the mean. So if you have high variance data, it varies far from the mean. That is going to impact your p-values as well. And so that'll tell you, hey, I'm not working off a nice normal distribution curve here. I'm going to be working off of something else. Okay, that'll skew. And so here we can say that the means, we cannot say the means are different. The means are equal. And so when we talk about p-values, and all I care about, we can talk about Pearson correlation, coefficients, and all that other stuff later, and we won't even talk about those in this class, is that we're going to look at those p-values and those two-tailed t-tests, because one of the things that you do in this class or any class is that you've got a go-to tool that you go to for statistics or GIS or anything. What's your go-to move? I was a wrestler back in the day. What was my go-to move when I needed points or whatever? Here, the two-tailed t-test is my big spatial tool that I use. Why? Because I can explain it pretty well. I'm teaching the class in it here. And so I don't get into other statistical tests. I'll talk a little bit about ANOVA, but these are kind of the two things. If I can get my spatial data into something that I can run on a two-tailed t-test, I'm happy. So I can categorically state that high-income areas have better air quality than low-income areas. Cancer rates are higher in low-income counties than high-income counties. That we can use this using the data that we state. And so the lower the p-value, the better. That little thing at the bottom that Excel squirts out for us, that's all we're going to care about and look at. Now we need to figure out how to extract that. And we're going to use, after the break, a nice little GIS function to run them. All we're going to do is just run a query, run a copy and paste, plop that right into Excel, and have that ready to go. And so if our p-values are between 0.05 and 0.1, we're 90% confident. If they're between 0.01 and 0.05, they're 95% confident. Anything less than 0.1, it's 99 or 99.9%. Remember we showed before last week where we ran that nearest neighbor analysis and it was like p equals 0.00001. That means we're really, really confident that those numbers are clustered. We're really sure they're clustered. Okay, when we ran that nearest neighbor analysis. P-value should never be 0, so P is approximately 0 for very extreme high P or Z scores. But this is an example of what we look at here. When you run a table or you run research or you happen to write a position paper for a class that you might be taking this semester, this is kind of what I look at here. And so when you start to think about research hypotheses that you want, we've got one right back there above Zanaya that said COVID rates near chicken processing plants are higher than COVID rates not around chicken processing plants. He did a whole poster and a whole paper just doing that. That's all we do. There's one in the back there where we have birth defect rates. Birth defect rates are higher in low-income counties compared to high-income counties or non-low-income counties. Don't even have to be high, but just non-low-income counties or counterparts. Okay? So all these things that we can look at here. Okay? We just did a paper and it's posted in modules, and I'll probably look it up after the break, where that we looked at African American female breast cancer rates were statistically different than any other race or ethnicity. Okay, now I'll let you all figure out the why on that. We'll figure out the statistics for these. But now when we ran spatial statistics and we extracted out hotspots, here are hotspots in the state. Here are cold spots in the state. So basically, by male rates were 9.04 in the hot spots. By male rates were almost 11 in the cold spots. It's actually opposite of what we were thinking, right? You would assume that COVID rates, you would expect by male rates to be much higher in places where there's more COVID, right? It's the exact opposite. And the way that I signify it with these little stars here. So I ran this little tool. Instead of me saying like p-values, I just say, hey, the p-value is less than 0.01. P-value is less than 0.01. P-value is less than 0.01. And you can see I am 99% sure that COVID rate by male rates are statistically different using our sample size. These sample sizes are a little bit different because I had 143 cold spots, 121 hot spots, and then a month later I had 163 hot spots and 154 cold spots. And then we did emerging hot spots and emerging cold spots. So areas that had areas that had increased, were emerging hotspots were like twice half the by mail rate of their counterparts that had no COVID. So the areas that were actually decreasing COVID were mailing at even faster rates than the other areas. Now, why? Why are areas with high COVID not mailing in their ballots? The rural areas, first of all, right? And so, as Naya said, she was talking about the idea of COVID rates being higher in rural areas. You know, it could be for another number of reasons. You know, access to COVID, politics, availability, all these other things, which would be kind of tying the same thing as what, polling places. Do you even have the resources to mail it in? It's really easy. I'd rather mail my thing in. But these are some examples. Here's another example right here here are my rural food swamps, those areas in red. Here are my best access. And then you can see the little stars where they are different based on income, percentage of people who receive public assistance and food stamps, rentals, percent minority. And so you can see those areas in red the areas where there's lots of fast food, it's 61% minority versus 43% minority. What do you think the chances are? It just happened to be 20% more, almost 20% more. Do you think that's a big chance or small chance? Really, really small. Like literally less than a 1% chance of that happening. Okay. And same thing with other. You can see here it's 93,000 versus 82,000. It's not significant, but that might be because not only the sample size, because the variance of the data. We might have highly varied data, which is going to skew your margin of error. That'll skew your margin of error. So a couple other things I'll mention here. Now we have the idea of equivalence testing, meaning that one of the challenges, this is taken from one of my papers here, so I'm kind of impressed with it here. But when we run statistical tests, insufficient evidence to reject the null hypothesis may not necessarily imply they're similar. Okay. And it's a little bit circuitous or whatever, but we have some things that are where we can run tests of equivalence, meaning like I'm not trying to disprove that they're not equal. I'm trying to prove that they're equal. Okay. I won't get too much into those, but I ran some of these things through R. Has anyone heard the term R before? It's a programming language, statistical programming language that has these things called tests of equivalence. One's called a test 2 one-sided t-test, which basically switches the null and alternative hypothesis. The other thing that I have is something called an ANOVA. It's called analysis of variance, which is basically a two-tailed t-test between more than two groups. So I want to see if there's a difference in rural versus suburban versus urban COVID rates or income, as opposed to just one versus the other. Or differences in high availability versus moderate availability versus low availability for certain metrics here. And so we can also run an ANOVA as well, meaning, hey, here is the average rates here. What are the chances they are statistically different right here? So for the unavailable, the good, the bad, p-value, what is this? 8.97 e negative 0.6. What is this thing Excel gave me? Is this a really high number or a really low number? Very low. Very low. What does 10 to the negative 6 mean?
6 significant, always significant, but 6.
Yes, 1 over 10 to the 6th, which is 1 millionth, right? Yes, 1 millionth. Okay, so 8.97 millionths. That's the p-value. Really, really, really small. We could go from 1 all the way down to past here. And so, once again, when we run these things, this is what I care about. this p-value right here. This is what I care about. Forget about all this other garbage. Learn that stuff in another class. No fun, no pun intended. But I care about this p-value so we can interpret these things. Okay, because F means something slightly different than the t value, and then we got Pearson's coalitions and within groups and all that other good stuff there. We can look at differences in income. Is there a difference between high COVID or food availability? I run a p-value 0.46. No, there's no difference here. You can see these two are kind of the same. This is slightly different, but when we run them all together, not necessarily. And the last example I'm going to talk about, like Benjamin was alluding to, we've got the different definitions of rural. This is the definition of rural using USDA. So when I ask what does rural mean, this is one definition of rural. Here's another definition of rural. Here's another definition of rural. Which one's the bestest or the rightest? So one versus the other versus the other. Now, I could do a little GIS magic and just superimpose them on top of each other. So you can see these areas in red satisfy 3 definitions in rural versus 2 versus 1 versus 0. But at the end of the day, this is just a map. Like at the end of the day, what we want to do is we want statistics. And any of you in our master's program, and some of the thing I was talking about with Benjamin before is, hey, we want to start running statistics, statistical significance. Some of the things where we tie in, what are the prices of bananas in high income neighborhoods versus low income neighborhoods? Do you think they're higher, they're lower, or more or less? I don't know. Let's find out. And when we run these things, if you don't get the answer that you want, that's okay. That's just another way to answer it. So if you're on a thesis committee and you say, I'm going to say that COVID rates are higher in rural areas than urban areas, and you don't get that, it's okay. Don't go around and manipulate your data so that you kind of get those. And so when we run a two-tailed t-test of income using one method versus the other, the rural is always going to be lower. Now, does that make sense? Yeah, isn't income lower in rural areas, cost of living, jobs, all those other things? So it's really kind of, you're answering these no-duh questions. Meaning that that makes sense. So when I look at this chart here, whether it's COVID rates, percent Democrat, this is a food access measure here, but I focus here on the left on income. These answer these no-duh questions. But now when I look at income or whatever else or COVID rates for each of these different columns, it's a little bit different. And so now when I look at COVID rates for these different definitions of rural, hey, difference is 0.38. Okay, that's okay. But when I run it for income, one definition of rural is 43,000, one's 40, one's 41,000. When I run this ANOVA, it says, hey, when I run ANOVA, the definition of rural is going to be different for income. Meaning, it's really going to depend on what definition you use. Like to me, this amazes me, meaning that they're statistically different. And so using one method, it's 43,000. Another method is 40,000. Using another method, it's 41,000. When I run this ANOVA for the sample sizes and the variances, they're statistically different. So when you use rural in one context, it's going to be different than rural in another context where income's different. And we sit there and throw around this word rural all the time, but we can look at 1, 2, 3, 4 of my 7 variables here have statistical differences across different food environment or socioeconomic metrics that we have here. No one's as amazed as I am. Boom, there goes a paper or whatever here. So let's take about 10 minutes here. We'll meet back here at 6:22. And what I want us to do is open up case study number 3. And we're going to ask some real direct questions, meaning is there a difference between COVID rates at the zip code level in areas nearer cities versus areas farther away from cities? So urban versus non-urban COVID. And maybe think about that, but we're going to open up exercise number 3, or it's called case study number 3. Hopefully it's up there. Is it under modules? I hope so. If not, I'll put it up there in the near future. Is case study number 3 under modules? Week number 8. Yes. Okay. It's under classwork. Because what I want us to do is run this, use our little GIS, and let's go and try to apply this. So we'll meet back here at about 6:23, 6:24, and we'll get started on this, and we'll have a nice pretty map open, ready to go.
I'm gonna just finish. Correct. No. I don't know, I don't know, I just. I don't know. Like, Already, I did not see it since some of the. It's okay. This is just let you, right? I did, sir. Yeah, I did. Over the job, they said. It started in the last, good and goes, but we go to like an hour, 30, he starts it, like, the. Then he just went over some parts, some of these, we grew up, where it was this.
Okay. I'm excited. Did you just get it?
Yeah.
Okay. All right, cool. Oh, real quick, let me go get my and while we're here, what we're gonna do is we're gonna open up case study 3. So where's my case study 3 here? We're gonna download it. I had it all set up, but you all noticed I had some issues right at the beginning of class. So we're gonna go to modules. And under week number 8, we're gonna click on case study number 3. And we're gonna download this, unzip it. Okay, I think we all remember the unzip stuff. And then open this thing up, and then I'm gonna go grab a marker here. And so make sure we extract it. Extract all. And then this will be sitting somewhere in downloads or wherever you specified here. And then from here, since it doesn't say extract up here, I'll just click on the case study 3. So I'll go get a marker real quick. We'll open this thing up. And so everyone here should have this open. I have some nice pretty purple maps. All right, so we're gonna start here. And while we're thinking of it here, if you want to, or if you can, open up Excel. So just get a nice blank Excel sheet, because you notice I was playing with it before with my Poisson distributions here. And so you notice this Poisson distribution here, this is the what it should look like. You get a true Poisson distribution versus what it looked like for Caswell County. You notice they're slightly different, but we can run something called a Kondratyov-Smirnov test. Try saying that 10 times. My wife loves to say Smirnov, but that's for another reason. Isn't that the vodka or something like that? She loves her vodka. But that's another issue. That's another issue in itself. But we can run something called the Kondratyov-Smirnov test to measure the difference between these two graphs when they're superimposed on each other, and it measures those with statistical significance. So, but what we'll do here, while we're here, we'll do File, and we'll create a new kind of blank right here. And then if you happen to have it, if you click on Data, you should have something over here that says Data Analysis. Okay, and when you open up Excel, do you have data analysis, Lauren? How about you, Ariel? All right, you got data? You don't. Okay, how about you, Benjamin? Do you have data analysis up in Excel? Okay, Excel. And I'll kind of show everyone how to put it on there, and those of you joining it, because we're going to use this data analysis. So click on the Data tab, and then all the way to the right, Data Analysis. Do you see anything there? No. Okay. So what we're going to do real quick, I better remember it right. Okay, and those of you joining us at home, because this is going to be a tool that you can use for anything. We're going to go down to File, Options, Add-ins? Yes, Add-ins, and then we're going to look for the Analysis Tool Pack. Okay, File, Options, Add-ins, and the Analysis Tool Pack. So click on that and click OK right there. Try it again. Go back to file, options. Right mouse. Click, let me try something else here. See what else we can add here. Got it. How'd you do that?
You just gotta click go.
Oh, I knew that. Click go. Okay. All right. And then click go. And then you can up in the top, you can click anything that you want. So there's VBA or whatever you want. But you'll see in the right here, analysis. We'll just click. Did you get it, Art?
Yeah.
Okay. Well, we're going to go back and forth with this computer and stuff. So. All right. Good. We got data analysis. So, file options. Group options. Let's go back. Click on go. Just check that. All right. So we're going to have this where we're going to bring it in. We're going to bring some data in and do some neat little statistics here. All right. So what we're going to do, this is a pretty simple question we're looking to answer, is that we want to figure out if there's a difference in COVID rates between cities and not cities. Okay, cities and not cities. And we're just going to run a nice simple two-tailed t-test. We're going to acclimate ourselves to the data a little bit. So you can see I've got 10 major cities sitting right here. You can see they go all the way from Wilmington to Greenville out to Asheville. I've got a reference map for North Carolina counties. And then I've got the COVID rates of June the 14th, 2021. So if I right mouse click on the feature class, open up the attribute, you can see what I've got here. I've kind of enabled and disabled a lot of these here. But you can see I've got COVID rates at the zip code scale. So you can see down here, there's 763 zip codes. You can see COVID rates of June of 2021, but you can see I've got 2021, 2020. If I go a little further to the right here, you can see I've got COVID rates. I got distance to the nearest store. I've got things like metropolitan, micropolitan, and rural. Has anyone heard the term micropolitan before? What's that? It was in my paper. Someone remembered my paper. Yes. You got an A for the class. Okay. All right. You remember. Micropolitan are going to be smaller cities that aren't surrounded by other big cities. So something like Greenville would be a micropolitan area because it's got the city of Greenville, which has more than 50,000 people, but it's not surrounded by anything that would have more than 50,000 people. Nothing out there. I got to go there Friday. For a retreat.
It's just easy.
Yeah, that's all I'm going for. Yeah. And so I've qualified these as metropolitan, micropolitan, and rural, and maybe think some ANOVA stuff. Also here I have zip codes, percent minority, percent Republican. Don't worry too much about these negatives. I think these are changes here. And like poverty rate. So maybe if, for like your paper, if you want to run some analysis like poverty is higher in rural areas compared to rural areas compared to urban areas. Maybe it's, I don't know, maybe, we can look at something, you can look at something like that, and you can write a paper on the two-tailed t-test that you run, the p-values and all that other stuff that we're going to run right here. And so the first question is that basically I want to compare the zip codes, 763 zip codes, near cities versus away from cities, further from cities. I'm going to write this down over here for the people kind of joining us as well as you folks here. I'm going to probably get in Benjamin's way here a little bit. Okay. And so I want to basically figure out the COVID rates. Now, the one thing is we're going to have a null hypothesis. Okay, a null hypothesis. Okay, so we'll put this H0, put a little colon right there. And one of the papers that I did post in modules on the African American female breast cancer mortality rates actually had the little null hypothesis written right there instead of me saying my thesis is going to be this. But we're going to say COVID rate in rural equals the COVID rate in urban. Now we're just creating binary classes, meaning we got urban, we got rural. We don't have micropolitan, suburban, or any of that other stuff. And then we have the alternative hypothesis, which just said the COVID rate in rural does not equal COVID rate in urban. Okay? So all we're trying to do is just prove or disprove one or the other. You know, and so it gets into some of the semantics involved with this right here. Hopefully, I think you guys can see it here. But we're just going to prove or disprove these statements right here. Now, my first question is, we've got 763 zip codes. They're either going to be rural or urban. We're not going to do like ones or the others or whatever there for the sake of this, because we can go and divvy these up. So first of all, what's the definition of urban? What's the definition of rural? How are we going to define it? How can we define it in a GIS? And since I got these nice red dots up here, maybe we can use these for reference. Alonda, what's your definition of urban? More than a certain population. Okay, that's a good idea. All these red dots are cities that have high populations. So what would you say? Any zip code near these red dots, right? Any zip code near a red dot. What's near mean? What's your definition of near? 5 miles, 10 miles, 20 miles? It depends on the research. Let's pick on someone who's joining us to see if they're around here. What does James say? Hi, James. What's your definition of near for rural or urban? I just saw him before.
I would say probably about like 15 to
15
miles.
miles. Good. We're going to go with what James said. James said 15 miles. So urban. Anything within 15 miles, any zip code within 15 miles of city. So less than or equal to 15 miles of a city. Then basically, rural is just going to be anything else, right? But we can divvy these out, however we want. Like Lauren said, we've got, there's lots of research out there as to, distances and all these other things. And you notice I did have a category here that based these on the county where it's micropolitan, metropolitan, rural, or whatever else. And so if we've got time, we would run an ANOVA related to that. Now, those of you, do you know how to pick any zip code within 15 miles of a city? I hope so. This is like intro level GIS stuff. So what we're going to do here is we're just going to run a nice select by location. We're going to find zip code data within a distance of major cities. And we're going to do what James said. James said 15 miles. We're going to go with what James said. And what do we see here? This is within 15 miles. Now, there's also qualifiers within, entirely within 15 miles. That's going to be something totally different than within 15 miles of it. Just part of that zip code is within 15 miles. Because right now we've got 208 zip codes that are within 15 miles. Now, you know what I'm going to do? I'm going to cut and paste those straight into Excel. Watch what I'm going to do here. So I'm going to go down to the bottom and I'm going to click Show Selected Features. Or up here, I could click on Copy Selection. So Show Selected Features. Actually, I'll go back here. Do I have a copy right here? No. All right, I'll go back to here. I'll click on Copy Selection. Watch what I'm going to do right here. I'm just going to copy, paste it right in. Look what I just did. I cut and paste every single zip code straight right in. And look what I have here. 209 sitting right there. I've got the names, I got metropolitan, I got micropolitan. Look what I've got here. So all I did was just cut and paste them right in. Okay. Now, next I want to pick, I'm going to do some quick math in my head. The 565 that don't belong. How do I do that? I could do something called reverse selection or switch. So I'm going to click this little switch button. Look what I just did. What do these represent? Everything else. Just like James said, everything else. How do I cut and paste that into Excel? Same thing. I'll click copy. And I'm just going to, in Excel, what I'm going to do is I'm going to add a new tab or a new sheet at the end. Just cut and paste it right there. So now I've got COVID rates. So what does sheet 1 represent? All the zip codes within 15 miles. All the zip codes outside of 15 miles. And in full disclosure, you know what we could have done? Full disclosure, you know what we could have done here is I could have gone over here, do my statistics right here. Now I see my statistics and do the same thing, but guess what? I don't have. I'm not going to be running the t-test. I can't run the t-test. I'm going to be running a t-test while we're here. See here, my selection, this rural has 850, or this urban has 850. Look at this slick stuff I'm doing here. Well, it's 878 for the rural. You notice what I just did there? I ran a switch and then I updated the properties. Now that's all good and well. So for my urban, it's about 850. For my rural, it's 878. I ran this using the descriptive statistic that we've already learned in the first half of class. What we're going to do now is take it a step further where that we're going to have to run that 555, or you can see I've got a couple nulls right there. And so those 560 versus those 209 or whatever, and see if these are statistically different. What are the chances that I went and measured the height of 209 faculty and measured the height of 565 students, and they were the same exact height? We'll see. You know, is it enough? Is this 28 going to be enough of a difference for me to say that? And ArcGIS Pro doesn't do that. That's where we bring in that data analysis tool. Okay? And that's where kind of the rubber meets the road when you start to go out and write papers. You know, I care about papers. I don't know how many of you care about papers, but when you go out and write a paper or write a thesis, or you go to your boss or do something interesting with statistics where, hey, this is statistically different, or they're more, but they're not that much more. But what you do? You can do them over different dates. And so if you want to write a paper entirely on this to say, hey, let me look at the difference in COVID rates throughout the time that Maruti was keeping track of data, because guess what? You got the data for it. You have to go and recollect it. Okay? Why did we pick 15 miles? Because James did. Okay? I would have picked 10. No, I don't know. If it's right, we'll credit James. If it's wrong, we'll blame James. But he picked 15 miles. What if we moved it to 20? Well, we might get a little bit higher sample size, or margin of error might be a little bit different. But that's okay, and there's nothing wrong with that, because when you put together your paper, say, hey, I define urban to be anything within 15 miles of those red dots there. Those are the major cities. But like Lauren was saying, hey, some of these are based on population and population density, and you showed some maps before that had urbans and rurals, so we have those. And so what we're looking at in Excel right here is just a big Excel spreadsheet here. One sheet has got all the data sitting from 15-mile group. And if you really wanted to, I can rename it. This is, within 15 miles. And then I can change this sheet, rename outside. Miles. And so what we're going to do is we're going to compare COVID rates from the same day. Does it make sense to compare them from different days? No, because we're working with two different sets of data. So all we're going to do is compare COVID rates from two different days. And I think I mentioned the 16th or somewhere in November. So column F here versus column F here. And so all I'm going to do is, if I look at the averages here, you can see my average is 878. Like we pulled here, right? 878. Yes.
The data is off from true code rate because
Oh.
everybody tested for code.
Oh, I know. I think it's way off, personally.
Some people just didn't care, or they were asymptomatic. So it's fine.
Yeah. That Lauren asked a good question as about how do we know the COVID rates are this, consistent or whatever. When we run these, we're going to assume it's something called imputation in census. We're going to assume that the amount of people who didn't report or were asymptomatic are evenly distributed across all the zip codes. Even though there's probably research on that, but that's neither here nor there. How's that sound? Alondra's still looking. She doesn't even want to make eye contact with us back there. How's that sound, Alondra? Good? Okay, good. So we'll assume that they're going to be we'll assume that they're going to be different. And so now what we're going to do is we're going to compare the COVID rates from this column versus the COVID rates from the same column. Now, you could go and do it for poverty rates, per capita income, any of that other stuff. Because if you go to the statistics or you go to the data fields, you notice that I unselected a whole bunch of stuff. And so if you want to do your position paper on something like this, feel free to. We've already got the data sitting right there for COVID, poverty, percent Republican. We might say, hey, Republicans live more in rural areas than urban areas. You think that's the case in North Carolina? Maybe not. See, I don't know. Or a Democrat, there's a lot of rural Democrats here in North Carolina. Okay, so you can look at some of those on the political landscape as well, those of you who are interested in it, because I went and collected the data. The one thing I would ask you to do is come meet up with me so that you can show how I got the data, as part of your methodology. So without any further ado, what we're going to do here is we're going to click on data analysis. And when we click on data analysis, we've got all these tools that kind of come up here. We got ANOVA, two-factor. You just heard me use the word ANOVA, right? Yeah. So we got that ANOVA. Now that's something different. That's a two-tailed t-test for more than two groups. And so if we've got time, maybe we'll look at that. histograms, F-tests, all that other good stuff here. Okay. What we're going to do is we're going to click on t-test, I'm sorry, t-test two sample assuming equal variances. Okay, t-test two sample assuming equal variances. Typically paired t-tests are going to be things like things that are paired over time, like what is your weight? You know, you have my weight at one time, you have my weight at another time, and we run some tests. You know, you put me on some certain diet or whatever, and how do I go up, do I go down, do I stay the same, or whatever. And so you're basically paired with something. These things are going to assume that we have two entirely different samples. You know, and all we're going to do is, what are the chances that the average of 209 COVID rates are 850 versus 565 COVID rates that are 878. That's all we're going to do. And so we've got the two-tailed t-test. Let's click OK. And then what do we have here? Variable one range. All right, let's click variable one range. I could click labels. That shows it's got labels here, but I'm just going to pick, what's my first group of data? I'm going to go pick everything from F2 all the way down to F209. Right? And my next variable is what? The outside 15 miles. I'm going to go from F2 so you can see what this looks like here. Oops. Let me click OK. Uh-oh. Contains non-numeric data. This is where we get into the idea of data cleaning. What's the non-numeric data we see here? Anyone see it? Let me cancel this real quick. Do you see any non-numeric data here? What do you see?
I think you highlighted the title.
Yep, I highlighted the title. In addition, yeah, I did highlight the title, but when I clicked on it, I made sure I didn't include it. But what do you see here? I see the word null. How do I get rid of those nulls? Do we just want to go delete those? What can we do? I can click on the F, click on Control H. I see the word what? Null. I'll just replace it with a, for now, I'm going to replace it with a 0. Why is Benjamin shaking his head? Oh, it's a value. What else could I do?
I'm not sure how Excel responds to blanks.
Okay. Well, let's see what it does. Okay. All right. Benjamin had a really good idea. If I hit Control H instead of null, I'm just going to just left it blank. That's a good idea.
I don't use, at home, I don't use Excel, I use Google Sheets. Google Sheets treats a blank as it's correct.
Okay.
So I don't know if Excel is the same or not.
I'm not sure. We're only working with 11, so in a normal situation, what I would do is I would go and sort and then just delete those null. I'd go and delete those null columns and not calculate those. For now, we'll just leave them blank. We'll rerun this thing, see if it yells at us. If we go back, we'll just sort and get rid of those. And those are some of the challenges that you have in working with real world data. Even we work with census data, you get zeros and nulls and stuff that has small sample sizes that will refuse to publish. All right, so let's run this again, data analysis. Here we go. Oh, okay, so we got this. F. Excuse me. So column F down here. All right, let's try this one. Let's see what it does. All right, okay. What do we have here? Variable 1, those were the urban, 850. Variable 2, 878. Okay, good. Observations, I've got 204 versus 548. We had about 11 nulls. I think there were 4 nulls in 4 nulls with my urban, about 7 nulls with my rural. We got rid of those, and it looked like it didn't treat them as observations at all. So Benjamin's right, where that we is just we don't have 763. We've got 752 or whatever. All right, fold, hypothesis, degrees of freedom, T stat, P, critical T. What I care about is this thing right here. Okay, and we're going to leave it right there. We can do one-tailed t-tests. We won't focus on those. We're focusing on two-tailed t-tests that look at basically both sides of your normal distribution or your histogram right here. This p-value says it's 0.311. Can we say that these two values are statistically different? No.
My numbers are a little off.
Your numbers are a little off. That might be it.
Like, just a little.
Okay. Because you picked 203 instead of 204. That's okay. And Lauren had one, and this is for everyone out there, and as well as those joining us. Lauren had 203, so her number was slightly different. Did you get a slightly different p-value?
Yeah.
Like, it's probably like point
0.28.
0.28. And so it looks like maybe one of those you missed was probably a major value, either like a 0 or a really high value. So I like this here. We can do everything except for run these. Now, James, what if I said 20 miles? Do you think we're going to get different values there?
Probably a higher.
Maybe higher is in terms of like 0.5, 0.6, 0.7. And so our hypothesis is that as we expand out further, our p-values might increase more, which basically means that these COVID rates get closer and closer together. So even though it's 878 and 850, we can't say they're statistically different. But we can run another one here if you really wanted to. Just for the heck of it, look what we have over here. We've got poverty rate right all the way to the right here. Hey, let's see if there's poverty rates are different in rural areas versus urban areas. This is just percentage of people who live in poverty. Poverty is based on what? Family size and income. And so if you make $60,000 a year, you got a family size of 11, that might be technically, poverty levels as well as location. We were talking about the idea of Hawaii, where I don't know how people live in Hawaii because just everything is so expensive, or Alaska or other places like that where people live. So how about we take a couple minutes? Let's run the same thing, but instead of saying COVID rates in rural versus COVID rates in urban, you do it for poverty rates using column T. And then you could also look at things like percent minority. Is there higher minority percentages in urban areas versus rural areas using James's definition of urban and rural? Because I might have used 20 miles. You might have used 10 miles. And so we would go recalculate those. So take a couple minutes. I'll run it too here for those of us joining us, and then let's see what you get. We'll look at poverty rate. I know I'm taking a long time on these here, but I really want to go through this process because I want us to work a little more independently. So I'm going to do this. I'll give everyone a couple more minutes here. I got my answer. I'll change this view here. View.
So what I think I did, if we had it in the first time, the last time, this time I did.
Okay.
Yeah.
Is that what you got?
Yep. I don't have as many decimal places. Yep.
Yeah, it's just because the column is small, because I was gonna say that too. If
Yeah, you can.
the
What?
column is smaller, it rounds it up.
Oh, okay. Like that.
That's
Just
fine.
make it a little wider. Once you start seeing those negatives right there, you know you got real small numbers. Was that?
Yeah, I got the
Okay.
power of -6 or.
All right. Did you get it, Alondra? Oh, good. What did you say? What statement can Alondra make from poverty rates in rural versus poverty rates in urban? What'd you get? Let's see. What'd you get? What's this thing tell you? The lower the number, the better, or the better the food. Okay, so we ran this, and now this time we've gotten the mean for urban was 15% poverty rate. For rural, it was 18.3%, and so we ran it through a two-tailed t-test. Is this what you got also, Ariel? Still running? Okay. And so what we got here is we've got 208 observations versus 555. So we've got the complete complement of 763, which is a little different than what we did for COVID because there weren't a couple here. We got pooled variance, all that other stuff, hypothesized mean, degrees of freedom, t-stat, p-values. What I care about is this right here. And if you notice right here, this is half of this, but that's another issue in itself because it's just half of the normal distribution curve. But you can see this is 1.34 e negative 6, so this is 0.000000134. This is really small. Smaller means that these are different. Smaller means, so once we start getting this number under 0.1, these are statistically different. Even though they're only like 20% different, a little less than 20% different, they're still significantly different. And so a lot of times, and remember that paper where I used metropolitan and micropolitan, the whole focus of that paper was that there's a whole subsection of rural society that we don't think of as marginalized or disadvantaged, but it's out there. A lot of times when we think of blight or whatever, we kind of think automatically in the cities here. But when we look at urban, which would cities and then some suburban areas, we can see it's significantly more in rural areas than urban areas. And even the access to food and what we look at, low income, low access. Didn't I have a paper on that? I forget all the papers that I had you over. What's that?
Probably in there.
Yeah, it's in there. You had to check one of the things that was right. Okay, so we have this here. And so these are the statements that we have. So, when we had sat there and Alondra said, poverty rates in rural areas are significantly higher than poverty rates in urban areas. And what we do? We extracted it from a GIS, 15 miles. And we extracted it from a GIS that allowed us to do that. The last thing we can do, and I'll kind of not run it real quick, show us here, but we can also run an ANOVA, run the same thing. So now let's look at metropolitan versus micropolitan versus rural for, let's say poverty. Okay. Now there's a couple different ways we can do this. For me, let's think. What's that?
Wasn't there?
Yes, there is an attribute for that. So one of the things that I think we're going to do, I'll show you this here. I'm kind of working with some magic here, but I'm going to click clear and switch. And I'm going to copy this whole attribute table right into a new Excel sheet. So I'm going to click copy. And I'm going to pop this all into a brand new sheet right here. I'm going to move it over to the right. Oh. And now what I want to do is I want to look at the poverty rates versus metropolitan versus micropolitan versus rural. So I have a whole new column right here. You see this new column right here? Column N, and I want to look at the poverty rates in column N versus column T. Do we need any other column here? No. So you know what we can do? And we've got another one here called median household income. Do we want to look at median household income or poverty? Poverty, since we already worked with it? Okay. But, so you know what I'll do? I'll get rid of all these columns. And you know what else I'm going to do? I'm going to get rid of all these columns. I'm going to get rid of all these columns here. So look what I got here. I got a real small data set right here. Okay. And so I got a poverty rate. Is there a way that I can only show just the metropolitans or the micropolitans? Now watch what I can do here. I can do something called data, and I can run a filter. Now look what I have here. I got metropolitan, micropolitan, rural. So what I'm going to do is just look what I just did here. Did you see what a filter did? Now look what I can do. I can just cut and paste everything right here. So I'm going to call this metro. Oops. Meant that oops in a good way. So now I've got a column here for metro. Did you see what I just did? I ran a filter. Filter on metropolitan, and I just highlighted all of the poverty rates. Watch what I'm going to do here. I'm going to get rid of metro. I'm going to get micro. I'm going to do the same exact thing here. So now what we're looking at here is I've got all the zip codes that are metropolitan. I got all the zip codes that are micropolitan. I got all the zip codes that are rural. So now my null hypothesis isn't going to be the COVID rates equal the rural equals COVID rates in rural equals COVID rates in urban. It's going to be, I'm going to call it PR for poverty rates, that they're all equal to each other. So the poverty rates in rural equals the poverty rates in metro equals the poverty rates in micro. Because we might say, hey, poverty rates are evenly distributed across the entire continuum of urban to rural. So it's just taking this two-tailed t-test one step further. That's all we're doing. So now we can say, hey, for my three different definitions of rural, the poverty rates are different, or the poverty rates are the same. In theory, when we're doing research, they better be the same because we're applying rural, haphazardly. And so when we run the ANOVA here, and this is just for you guys joining us here, the poverty rate in rural equals the poverty rate in the metro equals the poverty rate in the micro. That's what we do when we run a ANOVA. That's all we're doing here. Okay. Now, when I go down to the bottom, do you think all of these are going to be equal to each other? No. Okay, the metro's got like more than half of these. So I've got these in separate columns. I might look really silly in a second here, but in theory, when you run an ANOVA, you want everything separately in a column. You notice before I had one versus the other. If I really want to, I could have sorted those and had them top and bottom. I could have just clicked out a selection, but I kind of created separate sheets for that previous less than 15 miles, more than 15 miles. And so once again, I'll go to data analysis. Up at the top, I'll run ANOVA single factor. And then my input range is just going to be, and I can click labels in first row if I want to, or I can, hold on. I better have this right. Okay. So now I can just go pick everything so that it's complete. And like Benjamin alluded to before, if it's blank, it's going to treat it as a 0. So my input range now is going to be 3 columns wide for the metro, the micro, the rural. I'll go all the way down to my last value.
It's actually easier for everyone, but you can actually just put ABC, drag over ABC and it'll work.
Oh, okay, cool. What better? You just dragged over ABC
Yeah.
and then all the way down? Okay.
You don't have to go down, but
Okay.
you can just do that.
Oh, okay, cool. And it'll figure out, it won't go all the way down. Okay. Now, what do I have here? Sum, average. What do I have? Column 1 was my metro. Which is 15.8%. Column 2 was my micro, 18.9. Column 3 was my rural, 19.1. You can see, what does this p-value tell you? Are they different or are they the same? They're different. These are different. So I can't say that the poverty rates are evenly distributed or equal amongst rural, metropolitan, micropolitan settings using our definition. And so for your kind of paper that we're going to do is, these are the type of things I want you to run. Now we can run these, extract these from these were all extracted from GIS data. Did we do anything groundbreaking in GIS today? No, we did a select by location. We opened up a table, copied it to Excel, and ran a couple of the tools. Nothing too groundbreaking. It's just a matter of running stuff in the right order. So that's about it for me here. Basically, what you're going to be doing is you're going to be calculating cancer rates at the county level. You're going to be doing the same exact thing, but cancer rates at the county level for rural North Carolina versus Charlotte area. And so you're going to calculate cancer rates and see if we can say that the cancer rates in rural southeastern North Carolina are the same or different than cancer rates at around the Charlotte area, who may have better care or more urbanized or whatever, better access to healthcare, richer, more resources or whatever we want to use. Right, so I'll let everyone kind of take off with that. I'll post an announcement tomorrow. I'm going to be out of town on Friday at a retreat for a grant that we're working on. So I will be unavailable then, but this is really neat stuff. This, to me, I'll kind of talk another minute and then we'll all head out here. This is where the rubber meets the road. This is where you, as an environmental scientist, or a geographer, or a historian, or psychologist, or whatever, this is where you make or break your research hypothesis. You know, people in rural areas have less access. We know that. But some of these ancillary things with access to unhealthy food or better proportion of unhealthy food, poverty, some of these other things, air quality, water quality, all these other things that can be divided between distance, suburban, urban, distance to school, distance to point source pollution. These are all things that can be measured in a GIS and then extracted out to Excel. There's also other tools like SPSS, SAS, that'll run this a little bit better, a little more comprehensively. Also R, which is open source, but the tools that we're using in this class integrate the GIS with the statistics, so we're not doing anything too groundbreaking where we're going to need to bust out any of the more robust statistical tools, but no, they're out there. You know, you go to SPSS or SAS, I've used SPSS before, they've got, you know, two-tail t-tests that you can run, and then all you need to do is just bring in the Excel or bring in the CSV file, because we can convert all these things and do this as well. So more robust tools will probably give you a little bit more insights on the data, but I think stuff like this is enough that we can prove or disprove everything. And so for moving forward for your position paper, think about what you want to prove or disprove, whether it's SIDS deaths, COVID rates, birth defects, lots of things out there. V, who was one of our graduate students, she wanted to see if there was a difference between suicide rates pre-pandemic and post-pandemic. Really neat. So she took all the suicides and then measured the rates at the zip code level for all 763, and then she ran up. I don't think no, it wasn't a paired t-test. It was a two-tailed t-test because it was going to assume that these zip codes were independent of each other, not paired where they're related to each other, but ran an independent t-test like we just did to figure out if there was significant increase. And she said there was an increase, but she got a p-score of like 0.13. What does 0.13 tell you? It's close to significant. It went up, but not up enough for us to say it's significant. You know, it went up. It definitely went up, but just not enough for us to prove or disprove our null hypothesis and accept the alternative hypothesis. So that's enough for me today. Have a good week. Be on the lookout for an announcement for me tomorrow, and we should be good to go.
It's not a question for your class.
Oh, okay. And I'll stop.
You said, I think I missed something. You said you're going to be out of town when? When up?